Good afternoon, and thank you for joining us in this late session. I'll try to keep it light, and at least on the scientific part, both because of the hour and because I'm the guy in charge of IP protection in our company. So I call this little talk Deep Learning for Crash Test Dummies, which is a bit of a spoiler about what we're going to talk today. But the main idea here is how we utilize deep learning and machine learning in order to bridge one of the largest gaps that we identify in modern medicine, which is the gap between the automotive or the vehicle and the medicine. And you're going to see in the next few slides what is the problem, how we solve it, and what happens when you deal with real life. So my name is Gilad. I'm a co-founder and CTO at MDGo. MDGo is a startup company, a post-seed company with offices both in Haifa and Tel Aviv. We have been established a year and a half ago, and we're over 20 employees today. And when I'm saying over 20, I mean 21. And the company, when you talk about its technology, stands on two legs. The first one is medicine, and trauma medicine, to be precise. And the second one is obviously deep learning. This is why I'm here. But it's important to understand that deep learning rarely stands on its own when you talk about real-life problems and gaps. So we do have domain expertise in all of these. So signal processing, biomechanics, and vehicle mechanics, which all supports the problem itself. And I hope it's going to be clear once we're over today. So let's talk about the problem that we're trying to solve. And if you do not come from the trauma medicine field, like most people, this might not be familiar for you. But when you talk about car crashes and vehicle damages, the gap of information is huge. If you walk into any trauma unit in every hospital, both in Israel, but also in the US, Europe, Japan, and so on, you'll find out that 50%, give or take, of the people who are hospitalized in each moment came from a car crash. And yet, there's no information flowing from the car to the hospital. So this is the gap that we were talking about. And if you go into numbers and the implications of this, you find out, according to the European Commission of Transportation, that 44% of the people who died in car crashes could have been saved if only real-time information about their injuries, type, and severity existed. So that's a huge number. That sums up to tens of thousands of people who could have been saved each year worldwide. All right, so why? Why is it like that? Because if you look on the left side here, this is what we know right after a crash. So we know how the car looks like. Seldom it looks good. And this is one example. The problem with looking at the car is that it doesn't tell you much about what has happened to the person inside the vehicle. In fact, there was research 2 years ago. They gave doctors, traumatologists, pictures of vehicles and asked them to tell whether the person inside the vehicle should be evacuated to a level 1 trauma center, which is the highest ranking of level 1 trauma treating, or not. In other words, if the injury is severe or not, the accuracy was 50%, so it's like a coin toss. And the other things that we know is how the person looks like. But unfortunately, as cars are more and more safe and you have active safety features inside the vehicle, the trauma is less penetration and more blunt trauma and internal damages. So the other thing that has been used since the 1950s is what you see here on this poor person abdomen, which is called the seatbelt sign. This is an indication about internal bleeding of the abdomen cavity and chest. The problem is that the correlation between this and the actual injury is 15%, which is very bad. And in fact, if you look at a person who looks like this, which might not seem very severe, what's hiding inside can be internal bleeding on the abdominal cavity, which is seldom detectable in MRI and imaging if it's in the back cavity of the abdomen. And then this person may die in a few hours, up to 24 hours. The third thing that we know, and this is from the last year, is what you see here on the bottom, this graph, which is the vehicle accelerations you're using during the crash. This is one of the sensors that are available today, and we're going to obviously focus on this, so I'm not going to talk about this anymore. So on the right side, this is what we want to know in order to save these lives, these 44%. We want to know what are the exact injuries, what could kill a person in the next few minutes, few hours, few days. We want to know what kind of ambulance to dispatch. Here in Israel, we have 3 types of ambulance. We have the basic life support, which is the white, the advanced life support, which is what you see here, the yellow ambulance, and we have helicopters. And it's very important to allocate these resources wisely. And this is one of the main problems. And the third problem here is that we don't know to what hospital to evacuate. And this is a very key factor in saving lives, because if you suffer from traumatic brain injury, you need to be evacuated to a level 1 trauma center who have a neurosurgeon. Here in Israel, we have 27 hospitals across the country. Only 6 of them have is a level 1 trauma center. Hadassah and Karem, right here on this picture, is one of them. So this is the main approach of Endigo. We utilize the sensors inside the vehicle, so you saw acceleration data, which is one of them, but also seat occupancy, vehicle sensors of any type, temperature, and so on. We use the existing connectivity of vehicles, and vehicles today are luckily more and more connected in real time. We are a SaaS company, so we do cloud processing of this data that's coming out of the vehicle during crash, and we give insights both for insurance companies and obviously for trauma, whether it's the EMS. Here in Israel, we work with Magen David Adom and hospitals. So we're going to focus on this left branch to the rest of this talk. So we're not the first one who try to look at data coming out of the vehicle and try to predict what will be the injuries. Since the 1990s, there were a few researchers and a few products that did that. Basically, the approach was, let's look at the physics of the vehicle crash and try to predict the injuries. So they found out that delta V, which is the velocity that the vehicle have gained or lost during the crash, is the best predictor of what's going on inside the person. So they look at medical reports, they look at delta V from different crashes, and did this regression model, which basically tried to predict the probability of severe injury giving delta V. That was the best practice in the past 20 years. The problem is that even though delta V is a good predictor, it's not very good. And you see a few quotes here from different researchers. It says that, for instance, the first one, the force applied on the occupant head is anyone's guess giving the delta V. So it's obvious there is still a problem, and you can't be very organ-specific using delta V. So what we thought is, what if you can measure the human rather than the vehicle? Because the vehicle does not say much about the injuries. So we started to look at the options. The first one is in-cabin sensors. This is very intuitive. If you have monitoring inside the vehicle, if you have acceleration sensors in the headrest, if you have in-cabin camera looking at the person, it'll be very helpful. The problem is that they are not around yet. And we wanted to solve this problem right now. The second thing is that they not actually measure forces. It's very hard to measure forces in real life during a crash. So we looked at the other option. What are the existing sensors today? And we got back to square one, because the existing sensors today, they measure the vehicle. So we understood that there is something else that has to be, and you know what's coming, deep learning. So what deep learning can be applied here? So we, that was a spoiler. So we looked at crash tests. This is a crash test that we did half a year ago. And the good thing about crash tests, it holds both data, both the acceleration and exactly what happened to the dummies here. So meet the data. What you see here on the left is the acceleration, the same one that we saw in the earlier slide. This is what is measurable in real life. And if you look at the two right examples, you see the neck force on the dummy, applied on dummy, and the head accelerations. These correlate pretty well with the injuries, because now you have actual measurements on the human body, or dummies in this case. So the thought was, okay, let's try to predict one from the other to shift this domain. So basically, this is the approach. We say that in a car crash, there are 3 collisions, actually. First one is the car colliding with whatever is around it. So a barrier, in this case, it could be a tree or another car or whatever. The second collision is the person colliding with whatever the surrounding is. And as cars are more and more safe, the points of contacts are more predictable because you have the airbag, you have the wheel, and you have the curtain airbag, and you have the headrest, and so on. That's the second collision that we try to measure using deep learning. And what you can see here on the right, the blue curve would be what we call the crash pulse, the acceleration of the vehicle. The purple curve is what is measurable on a dummy. And what we try to do is to predict it using the blue curve. So that's pretty much the idea. The third collision is the trauma. It's the internal organs colliding inside the cavity of the body. And we do this by using state-of-the-art biomechanical models. I'm not going to go into that. I'm going to focus on what we call virtual sensors, try to predict dummy sensors using the crash pulse. So not surprisingly, we turn to LSTM. We use crash pulse together with crash attributes because there are other data that should be taken into account because crashes are different from one another. For instance, frontal crash is significantly different than a side crash. It should be taken under consideration. And we predict what we call virtual sensors, which I talked about earlier. So this is the basic idea, and that's the deep learning that we do. But the question that should be asked right after that is how well are we doing, and how the hell do we get the data to do that? So this is an example from a crash test. You can see here the blue curve is the ground truth. It was measured on the dummy, and the orange curve is what we try to predict or manage to predict. And this is very impressive if you talk about the implications and how well you're doing. Remember, we're comparing to methods from the 1950s with 15% correlation. So let's talk about the data, because obviously you need a lot of crash tests, and crash tests are very expensive. I can tell you that firsthand. So the first thing that we looked at are open databases of crash tests, because at least in the US, if you're a car manufacturer and you want to do a crash test, the crash test is recorded and it's open to the public. The bad news about these is the regulation requires only 3 to 4 scenarios, which are specific velocities, specific barriers. So the diversity is pretty narrow. What you do get is diversity in the car models. So we understood that we have to look at more and more examples, more angles, more velocities, and more human body models. So we took it in-house. So the first thing that we did is we purchased a license for finite element modeling of vehicles. This allowed us to do pretty much whatever we want in terms of scenarios under the envelope of the simulation capabilities. So this is one thing that we do. This is a very simple example of simulated crash with finite elements. The second thing is we validated some of the out-of-the-scope simulations with crash testing. This is the one that you saw earlier. This is a crash test that we've done 2 weeks ago in the Netherlands in order to look at other attributes of a crash. So this is far from what you see in the regulation in the regulation scenarios in terms of the angle and the velocity. What's interesting about that is the white car here. We put a baby dummy because when you see crash tests that are required by regulation, it's always the 50 percentile male. So we used, in this case, both a dummy of a baby and a woman. But the other thing is that because the scenario is out of the ordinary, we got results, and you can see here on the bottom, that you never see in crash tests that are required by regulation. You see that the passenger on the red car got tossed to the side, which is another type of injury than you can see in the usual crash tests. So when ideas meet real life, so up until now, it was all very nice in theory, and we looked at lab results, and we looked at very good quality of sensors. But when we talk to what's available today in terms of sensors and connectivity, you start to see things that are less than optimal. So if we compare crash tests from lab in real life, for instance, the sensor location in crash tests is welded to the center of gravity in a very rigid place, which is very comfortable. But when you talk about aftermarket devices or even OEMs, car manufacturers, they do not necessarily put those in these convenient locations. Telematics companies, or companies like here in Israel, you know, E21, Pointer, Trafilog, to name a few, and you get an aftermarket device with a sensor placed on it. And it's usually in weird places like the glove box, the dashboard, or whatever. So you have to do some kind of a domain adaptation between what you know from the crash test and what's going on in real life. The sampling rates are much lower. This is why we have signal processing people, but also we use machine learning to do some kind of adaptations because we lose a lot of data. Dynamic range is a problem because standard acceleration sensors in vehicles go usually up to 16 Gs. Some of the severe crashes go up to 25, 30 Gs on the vehicle, and then you have some kind of trimmed signal, as you can see here on the left side. In this case, the sensor was up to 8 Gs. So we have to do also peak reconstruction, which is also, we also solved it with using a machine learning method. The events detected are always crash when you do a crash test, but in real life you get other weird stuff. You get bumps in the road, you get a person who thought it was a good idea to drive into to a forest, and then the car is all bumpy and you see a lot of false alarms. So detecting that there is actually a crash is a problem that you don't have in a lab, but when you go into real life you see that. And obviously the occupants, and I talked about the crash testing that we do with other human models, this is also a problem when you talk about the real life. So these are all just to give you a taste of secondary problems that we solve using machine learning and deep learning, other than the main thing, which is the virtual sensors. This is just a summary to give you a high-level architecture of what we do. So first of all, we get real-time data from the sensors. 100 hertz, 16 Gs, all the problems that we saw earlier. First thing that we do is the pre-processing, peak reconstruction, data rates, modifications, and so on. Then we ask what has happened to the vehicle. This is very important as a side attribute. This is the first collision. This is why it's marked 1. What was the crash scenario? What was the velocity? And what was the damage to the vehicle? This is very important for insurance companies, for instance. Then we go into the virtual sensors, which is what we mainly talked about in the previous slides. But then we have the physics of what's going on per organ. So we know what the forces apply to the head, to the chest, and whatever. And then we have to translate it to do language that doctors can actually read, because if you say to a doctor, this person suffered 50 Gs to his head, I would say, okay, really? So we use biomechanical analysis, and state-of-the-art, we actually collaborate with one of the leading universities in the US that does that research and have applied biomechanics lab, University of Virginia. In order to translate forces into medical meaning. We do it by extracting the physical attribute, extracting medical criteria, and eventually translating them into clinical scales. One of them is the abbreviated injury scale, which is standard in trauma units. This gives the doctors the data in the language that they actually speak. That's pretty much it. MDGO is operating here in Israel. It's connected to 250,000 vehicles on the road today, and integrated into Magen David Adom, MADA, the national EMS of Israel, with some successful POCs abroad in Europe, Korea, and the US. We would be happy to talk in person. Thank you very much. If you have any questions, please.